Hi, I'm Arnav, and I'm going to talk about our ITCS paper, New Bounds for Circular Trace Reconstruction, which is joint work with Paul Valiant and Hongyao Wang. The famous trace reconstruction problem is the following. Suppose you're given an unknown n-bit binary string x, which passes through a deletion channel. The deletion channel flips a coin for each bit of x and deletes the bit with some constant probability p. Here I've colored the deleted bits in red. When the channel is done, it outputs a trace x tilde, which is just the subsequence of x that's left after deleting the bits in red. The big question is how many traces are needed to recover the original string x with constant probability? And this really is a big question. It's been studied for 20 years and surprisingly remains open. There's an exponential gap between the best known upper and lower bounds, which is surprising because it's such a natural and easy to state problem. And the obvious question is, what makes this so complicated? Why is it hard to think about upper and lower bounds for trace reconstruction? Well, one possible issue is that deletion destroys information not only about the bits that are deleted, but about the bits that remain. What I mean is this. Suppose that we want to reconstruct the 3 bits in the very middle of this string, the green 101. A typical trace from this string might look like the subsequence at the bottom of this slide. But looking at this subsequence, it's not really clear what happened to the 3 green bits. It's not clear whether they were preserved, and if they were preserved, it's not clear where they went. In fact, it turns out that all 3 of these bits were preserved, which you should expect to happen with constant probability, since there are only 3 bits and the deletion probability is a constant, but they've been shifted by all the other deletions that took place in our original string. The moral of the story is that looking at a single position in the middle of the trace is not a very reliable indicator. In some sense, the whole string has been blurred by roughly root n by the deletion process, where root n is the standard deviation of the binomial representing the number of bits that were deleted to the left of 101. Okay, well, that was a fairly vague idea, but one way to formalize it is to think about what we can reconstruct. And one thing we can reconstruct is the first few bits in the trace because they have nowhere to shift. In particular, you can think about a constant size prefix of our original string, say the first 9 bits. And since these bits have nowhere to go to the left, regardless of what deletions take place in this string, their location is going to be preserved. And since there are only a constant number of bits, they're all going to be preserved with constant probability, so a constant number of traces suffices to reconstruct this prefix. And a natural question is, does the shift make reconstruction strictly harder? Or, in other words, is it really the complicated thing about trace reconstruction? Well, one way to answer this is by asking, what if everything shifts? Or, in other words, what if there's no prefix? This is the circular trace reconstruction introduced by Narayanan and Ren. And in this problem, I'm going to ask you to imagine that the string has no beginning or end. It's just a circle. And we can delete bits from this circle in the natural way by flipping a coin for each element. And what's left is a circular trace, again with no beginning or end, that's a subsequence or maybe a subcircle of the original string. If circular strings make you uncomfortable or you think it's hard to think algorithmically about these objects, an equivalent way to view this problem is to add a random cyclic shift after the deletion process. So here's a linear string x. We pass it through a deletion channel and it happens to delete 3 bits. This yields some trace x tilde 10111. And before returning this trace, we apply a cyclic shift, which moves everything 2 bits to the right. And so the algorithm sees the string 11110. Now, of course, since the trace has been shifted, we can't hope to recover the original string exactly since we have no idea where it started and ended. All we can ask is that you recover x from traces up to a cyclic shift. So the algorithm is allowed to return any cyclic shift of x, and we'll consider this a valid answer. I should mention that one known result, also due to Narayanan and Ren, is that this is at least as hard as linear trace reconstruction. Essentially, given a linear trace, you can pad it and shift the result to create a circular one, and so any reconstruction for the circular version of this problem can also be applied to the linear version. It's not known whether there's any separation between the two problems. Our contribution in this paper is to give upper and lower bounds for circular trace reconstruction of sparse strings using a set of functions that we call cyclic statistics. And notably, since sparse strings are of course a subset of all strings, this implies new lower bounds for the general problem of circular trace reconstruction. But before discussing any of the statistical bounds, I'll start by defining the key concept of cyclic statistics. These statistics are useful for studying constant sparse strings, by which I mean strings with exactly k ones for some constant k. Since we don't care about cyclic shifts, each of these strings has the form 1 followed by x1 zeros, then a 1 followed by x2 zeros, and so on, all the way up to the last one followed by xk zeros. And this string and a typical trace from this string can both be represented as a sequence of gaps, x1, x2, xk, between the ones in the string. And this is the representation that I'll use from now on. The important thing to note is that since k is a constant, all of the ones will be preserved with constant probability. So for the rest of this talk, I'm going to ignore traces where the ones get deleted and just think about sequences of k zeros, k blocks of zeros that occur between ones. One natural way to characterize each of these sequences of blocks or gaps is using monomials, where each monomial is a product of some m gaps defined by an m tuple from the set 1 through k. But of course, we might see any cyclic shift of the sequence x1 through xk, so we probably want a quantity which is invariant to cyclic shifts, and the simplest way we can do this is to sum the monomial over all cyclic shifts of x1 through xk. And this results in some polynomial. If the polynomial has degree m, we call it an mth order cyclic statistic of x. The main result of our paper is that one can obtain upper and lower bounds for sparse circular trace reconstruction using just cyclic statistics. These statistics happen to characterize both the bounds for sparse circular strings. So the next part of this talk will concern lower bounds and their connection with cyclic statistics, which is the following theorem. Fix a pair of strings, x and y, where here pi of y means that x must be a permutation of y, which have identical cyclic statistics up to order m. Then, ignoring logarithmic factors, it takes omega of n to the m plus 1 traces to distinguish these two strings. The intuition for this is that since none of the ones get deleted with constant probability, we're just interested in the sequence of gaps that remain after deleting zeros from x. If we observe a trace a1 through ak, which represent the gaps in the trace, from an original string x, this trace might have come from any one of the k cyclic shifts of x. Fixing a single one of these shifts, the length of each gap in the trace is a binomial random variable, i.e. the number of bits deleted from x1, the number of bits deleted from x2, and so on. And each of these binomials is independent, so to get the total probability of observing a1 through ak, we multiply them. And this results in something that looks like the product of binomial terms summed over a bunch of cyclic shifts of x, which starts to feel like a cyclic statistic. And with a little algebra, we can transform this probability into a polynomial function of n, where n is the total length of the trace. The degree of the polynomial is k, the number of ones in the trace. And even more interestingly, the coefficient on the n to the k minus m term in this polynomial is a function of the order m cyclic statistics, in fact a linear combination of the order m cyclic statistics of x. And so, if you can find a pair of sequences whose cyclic statistics cancel up to reasonably high orders, you can cancel out the first several terms in this probability, yielding two probability distributions which are pretty close. We can apply this formula to the following hard instance, which is distinguishing two strings x and y with exactly 3 ones each, where the size of the gaps of zeros are n plus 1, and n plus 2 in two different permutations. Now, x and y are cyclically distinct, but they have identical cyclic statistics up to order 2. And since the two highest terms in the polynomial I just showed you cancel between x and y, we get two reasonably close probability distributions. Applying our lemma from earlier, we can get an n-cubed lower bound for these pair of strings, which recovers the best known lower bound, which in fact comes from this particular instance, proved by Narayanan and Ren. But we can go even further. We can generalize this result to any pair of strings. Here's a pair of sequences of length 12, representing strings with 12 ones each, which cancel up to order 4. I don't have much to say about this specific choice of digits or why we chose a sequence of length 12, because we found this instance via computer search. But the moral is that we can show a new lower bound of roughly omega of n to the fifth, which is not just a stronger lower bound for sparse strings, but the strongest known lower bound for all circular strings, and a new result enabled by our characterization of cyclic statistics. This, of course, raises the question of whether there are even harder cyclic statistics. How far can we go with this lemma? You could imagine two strings of length 1 billion with cyclic statistics matching up to order, say, 20, but we actually ruled this out. We proved that no such pair exists. Any two cyclically distinct strings of any length must disagree on some cyclic statistic of order at most 6. This is arguably the most surprising part of the paper, and the proof is via Fourier analysis, which unfortunately doesn't lend itself to a 20-minute talk. However, a result not only eliminates stronger lower bounds from cyclic statistics, it gives an algorithm for reconstructing any sparse string, which is the last section of this talk, upper bounds from cyclic statistics. So to begin, I should note that a standard strategy in trace reconstruction is to reduce it to a distinguishing problem. Given a set of traces, decide whether they came from x or y for a fixed pair of strings x and y. You can then test every possible pair x and y against each other in a massive tournament and pick the single string which defeats all the others in this tournament. This string will be unique if you take enough traces, and since there are only polynomially many strings with constant sparsity, the reconstruction problem is only a log factor more expensive than the distinguishing problem. So for the rest of this section, I'm just going to focus on distinguishing x from y for a known pair of strings x and y. Our goal will be to solve the distinguishing problem by estimating a cyclic statistic in which x and y differ. And as long as x and y are cyclically distinct, we know that there is some cyclic statistic of order at most 6 that we can use to distinguish them. So the naive first approach is to just estimate the statistic from cyclic statistics of traces in the natural way. Since the original sequence x and y are both integer sequences, we need to estimate the cyclic statistics to within constant error. Anything less than, say, 1/2 will do. But these estimators could potentially be quite noisy because their variance is high. Remember that the cyclic statistic of a trace, xi1 through xi multiplied by xi2 multiplied by all the way up to xi6, is a product of 6 binomials. And each of these binomials, in the worst case, might have mean and variance omega of n if all of the gaps in our sparse string are roughly the same size. And in this case, a back of the envelope calculation gives a sample complexity of about n to the 11th, which is much larger than the n to the 6th bound that I originally promised. So to solve this problem, it's worth looking under the hood at why the variance is so high. And the reason is that each of these binomials might deviate by square root of n from its expectation in a typical trace. So the cyclic statistic looks something like the product of a bunch of terms that each look like n plus or minus root n. Of course, the expectation doesn't have any root n's, so this statistic might, in the worst case, differ by something like n to the 5.5 from its expectation. To reduce this deviation, we could try to cancel out the n terms, which are the sort of cause of the high variance. And one way to do this is to subtract out the expectation of each binomial. But, of course, there's a new problem, which is that the cyclic shift makes it hard to figure out the expectation. We know the gaps, so we know what the expectation of x tilde 1 all the way up to x tilde k might be, but we don't know what order we're looking at when we look at a trace. We don't know whether the first gap in our trace came from x1, x2, or xk. And if we don't choose the right shift and the right pair of expectations to subtract, we might not even be estimating a consistent statistic, which makes it hard to guarantee that our algorithm will work. So the big question is, how do we know which expectation to subtract? Well, our solution is to cluster the gaps into groups which have radius roughly root n and which are roughly root n apart from each other. Since each gap stays within root n of its expectation by standard binomial concentration, the size of the gap never leaves its cluster with high probability. Another way to say this is that in a typical trace, we may not be able to tell apart two elements in the red circle, but we can tell reds apart from blues and blues apart from greens, which is good enough, as long as we define a consistent cluster center for each of the gaps in the red cluster, and each of the gaps in the blue, and each of the gaps in the green. We're able to subtract this common center from all of the red elements, all of the blue, and all of the green, and kill the n terms in the binomials. Well, this introduces a problem of its own, which is that subtracting a common set of centers from both the strings x and y might make them cyclically indistinguishable. Remember, we just promised that cyclic statistics are distinct, but now we've modified our estimator to be something like the cyclic statistic with some sequence subtracted from them. And if the sequence isn't a constant, we're potentially in trouble. So here's an example of where this could go wrong. Take this pair x and y, which follow the same sequence of centers, which I've highlighted in red and blue, s, s prime, s prime, s, s prime, s prime. But note that for x, the s terms in red correspond to an offset 0, so x has gap s over q plus 0, where q is the retention probability, and y has a gap s over q plus 1 in each of the s terms. So x and y are cyclically distinct. The clusters and offsets might be cyclically identical, but their alignment is the same. The problem, though, is that after we subtract the cluster centers s and s prime from x and y, we end up with two sequences that look like q times a cyclic shift of 0, 1, 2. And now we've erased any signal that might have existed in the original statistics from x and y, because we're just left with a pair of sequences that are cyclically identical, and we have no promise about the cyclic statistics. In fact, all cyclic statistics of the sequence are identical. So here's how we get around this last hurdle. We choose a canonical shift of x and y. Let's say, in this case, s, s prime, s prime, s, s prime, s prime. And when a trace comes in, we will cluster its gaps and then force the gaps to meet this pattern of clusters by shifting the trace again if necessary. Now, for example, in this case, if we cluster all the gaps correctly, and remember, clustering correctly happens with very high probability, since the clusters are far apart from each other, there are exactly two ways to get the canonical shift. You could start at either one of the red gaps, which in this case are x1 or x4. Since these two shifts, x1 and x4, are a distance 3 apart from each other, we say that the sequence of shifts ss prime, s prime, ss prime, s prime is symmetric mod 3. And more generally, a sequence of clusters is symmetric mod L if it's invariant to shifts which are multiples of L. If you shift this sequence ss prime, s prime, ss prime, s prime by any multiple of 3, you'll end up with the same sequence. Now, after we've lined up the strings x and y with the desired sequence of clusters, that is red, blue, blue, red, blue, blue, x and y will always differ if we're just looking at the remaining offsets, since the red in x always corresponds to a 0 and the red in y always corresponds to an offset 1. And this is a signal that we can detect efficiently since the size of the gaps differs by a constant between x and y when you restrict yourself to looking at these particular shifts. So our solution is to sum over every third shift of the trace, corresponding only to the shifts which yield the canonical sequence of cluster centers. This ignores the shifts which caused the confusion a few slides ago and guarantees that we'll see some signal in the difference between our cyclically distinct strings x and y. Formally, the algorithm relies on this lemma. So fix a pair of strings x and y, which are cyclically distinct, then one of two things is true. If x and y have a common cluster sequence S, as they did in our tricky example, and S is symmetric mod L, where L was 3 in our example, then x and y differ in some cyclic statistic mod L. In other words, if you sum over the shifts which are multiples of L, that's good enough to see a difference in x and y. If this is not the case, then x and y can be distinguished with a constant number of traces, since all you need to do is cluster the gaps and then look at the sequence of clusters to distinguish x from y. You don't even need to worry about distinguishing elements within clusters. This means that if we're in the first case, we can safely subtract s before computing any cyclic statistics without erasing any differences between x and y. This gives us a new statistic with variance roughly end of the sixth, which also implies an end of the sixth algorithm, since we wanted to estimate the cyclic statistics to within constant error. So here's one last summary of our results. Omega of n to the fifth traces are necessary for circular trace reconstruction, even for sparse strings. And this result is almost tight. In fact, roughly n to the sixth traces suffice for any sparse string. And both of these results, surprisingly, come from the same nearly tight characterization of strings in terms of cyclic statistics, which is that x and y can be distinguished in O of n to the c circular traces if and only if x and y differ in some cyclic statistic of order at most c, where the asterisk comes from the requirement in the lower bound that x and y be permutations of each other. It's not entirely clear whether this requirement can be removed or not. In closing, I'll ask some open questions about this problem. First, of course, how do we close the small gap between the upper and lower bound, and in particular, which one is tight? The difference comes from a technical number theoretic fact in our characterization of cyclic statistics of cyclically distinct sequences, and it's not entirely clear whether this fact could be generalized to yield an O of n to the fifth algorithm, or possibly whether there exists a more complicated sequence of gaps which yields an n to the sixth lower bound. Another question, of course, is what about non-constant-sparse strings? The best known lower bound for linear trace reconstruction uses non-constant-sparse strings, in fact strings with theta of n ones, and it's possible that this lower bound might inspire better lower bounds for the circular version as well. On the other hand, n to the fifth is already quite a strong lower bound, and there aren't too many natural problems where the optimal sample complexity is a high degree polynomial. So it would be interesting to see if we could either push this lower bound even further, or possibly whether trace reconstruction, circular trace reconstruction can really be done in polynomial time. And the final question is, what does this tell us about linear trace reconstruction? Linear traces are quite different from circular ones, and of course, we're not satisfied in the linear version of the problem with returning any cyclic shift of our original string. But our techniques from cyclic statistics yield much stronger lower bounds for circular traces than anything known for linear traces, and we use techniques which are quite different from what's previously been done for linear traces. It could be interesting to see whether any of these techniques are useful for the linear version of the problem, or whether they inspire any new constructions for hard instances of linear trace reconstruction. We certainly hope they do. Thanks for listening.